Storm Chasers. I'm Brenda, one of your cafe coordinators, and we're back with a Teen Science Cafe presentation. Before we go further, we'd love it if you subscribe to make sure you never miss another awesome NTM&S video. Remember to be respectful in the chat, as your moderators will be keeping an eye on the comment thread, and please leave your questions in the chat. You can also check out Teen Science Cafe Rally on Twitter, Facebook, and Instagram.
Tonight, we've got two exciting guests for you. Our presenters are Katy Hollinger and Morgan Bell from NC State University's Marine, Earth, and Atmospheric Science Department. They are both second-year PhD students studying hurricane modeling as a way to prepare for future storms. Please give a thunderous applause to Katy and Morgan.
All right, hello everyone. Thank you so much for that introduction. So like they said, we are Katy and Morgan. We're both second-year PhD students and we study hurricanes. So we're happy to share all of that with you all this evening. We wanted to start off with just kind of talking about our paths and how we got to where we are interested in weather and in grad school for weather. So growing up, I grew up in Southeast Pennsylvania in Lancaster. We got a lot of interesting weather, got thunderstorms, not very many tornadoes, but ever since I was little, I always loved watching the clouds and going outside every time it rained to run around in the rain and taking pictures of rainbows like shown here. I just was always interested. So when I was in about middle school, my parents bought me this kind of weather observing station. So I got to see what the temperature was like inside versus outside. It would tell me if it was sunny or cloudy. Humidity level, things like that. And so growing up, I was always the most interested in math and science. And as I was getting to the end of high school, I was trying to figure out kind of what I wanted to do in college. And so I took a meteorology course that was like a half-year class in high school. That was meteorology and astronomy, which are a little different. But so the meteorology part, I fell in love with. I thought it was the coolest thing, learning about hurricanes and tornadoes. And that really encouraged me to study it in college. And my parents also told me to do something that I was passionate about. And so that's kind of what drove me to study atmospheric science in college. And so I went to the University at Albany up in New York. I studied atmospheric science, which is just another term for meteorology, which is just another term for weather. When I was an undergrad, I knew I loved the weather, but I had no idea what I wanted to do. So I had all kinds of internships. I was really fortunate to do a lot of different things to test out all different kinds of weather jobs to see what I wanted to do. So I interned at the National Weather Service, which is the federal weather service for the United States. They have offices all across the country that put out forecasts, and they also give out warnings anytime there's any kind of severe weather as well. So I got to intern there. I also got to intern at the Office of Emergency Management for New York State. So that was where they had the responses to weather, and if there was flooding or heavy snow or something like that, they were the people that would respond to it and send the aid and things like that. So I got to see kind of the other side of what happens after the weather comes. And then finally, I interned at something called forensic meteorology, which is where they use weather information in court cases. So if somebody slips and falls on ice, they contact a meteorologist, and the meteorologist can tell them if there was ice, if there wasn't ice, and kind of aid in the investigation in the court case that way. And so all of these different experiences really helped me understand that I loved research. I loved learning new things and understanding how things worked. And kind of the best direction for me to go with that passion was grad school. And so my project here at NC State, which I'll talk about a little later, is really what brought me here to NC State. So that was kind of my path and how I got here into grad school. And now I'll pass it off to Morgan.
Hi, I'm Morgan. So what brought me to weather, I used to be very, very afraid of the weather. I lived in Minnesota for a while, and we would get really bad thunderstorms, and we would get the occasional tornado. And then I moved to Georgia, where we would also get really severe thunderstorms. So in order for me to always know what type of weather was approaching so I could prepare for it, I started obsessively watching the Weather Channel, so I would always know what was about to happen. Eventually, I decided I needed to conquer my fear, so I started learning a lot more about meteorology, which led me to taking a high school meteorology class. And learning all the information from that class, I decided that I wanted to major in atmospheric science, which led me to go to the University of Georgia, go Dogs. And there I was able to intern also at the National Weather Service, where I studied communication, and I learned about weather, and I learned about Hurricane Michael. And I also was able to get my foot in the door for broadcasting, where I did Athens, Georgia weather, where I learned a lot about the broadcasting side of meteorology. But I decided that wasn't really my thing, which led me to going to grad school at NC State. And now that I'm at NC State, I'm working with the National Science Foundation and our advisor, Gary Lackman, learning about hurricanes.
So now that you guys have heard a little bit about kind of what got us here, we're going to dive into our research and all there is to know, a crash course as much as we can about hurricanes for you guys. So as we said, Morgan and I both study hurricanes in grad school, and we study different aspects of them. But what exactly even is a hurricane? If you're not familiar with it, or if you kind of have an idea but don't really know what the technical side of things is, a hurricane is just a large spiraling system that has a low pressure at the center. And I'll pause for a second to explain. So low pressure systems are, if you've ever heard kind of your local TV meteorologist talk about low pressure and high pressure, low pressure systems are usually associated with rain and storms and kind of the bad weather. Unless you're a meteorologist, that's the more fun weather. But and then high pressure systems are usually associated with like sunny skies, clear days, things like that. So hurricanes are a large spiraling system of thunderstorms that are focused around this low pressure center. They're characterized by really strong winds, and they usually bring a lot of rain as well, because they just have a lot of moisture associated with them. In the Atlantic Ocean, kind of the storms that we deal with, we call them hurricanes. But in the Pacific Ocean, they call them typhoons. And in the Indian Ocean, they call them cyclones. The more broad term for all three, to just talk about any of them, is tropical cyclones. So we might flip back and forth tonight between tropical cyclones and hurricanes. In the Atlantic, our hurricane season goes from June 1st until November 30th. You can get hurricanes forming outside of that window, but that's kind of like the peak time that we're expected to see them. And so we also want to specify that these low pressure systems don't have fronts. So hurricanes don't have like cold fronts or warm fronts associated with them. They're just kind of this big low pressure system. And so talking a little bit more kind of about what makes up a hurricane. So what exactly does it have with it? You might have heard about the eye of a hurricane. That's the part that's clear. It doesn't really have any rain associated with it. It's kind of the main point that everything else rotates around. So that's shown here kind of in the middle of this storm. Right outside of the eye is the eye wall. That's where you have the strongest winds associated with a hurricane. In the eye wall, or outside of the eye wall, you also then have additional kind of rain bands, which are just additional kind of rotations around the storm that have precipitation and or a lot of rain associated with them. And between the eye wall and the rain bands, you have this rising motion from the ocean. And Morgan will talk a little bit more about that in a little bit. Something that's really cool with meteorology, we have really great satellites. So satellites that orbit around the Earth, and they take really high quality pictures and videos of different storms. So this is a satellite image of the eye of Hurricane Irma. And as you can see, it's really clear in the eye compared to everything else. So you got the white clouds all around the outside of it, but the middle you can actually see down to something dark, and that's the ocean surface.
So now that we've talked about what a hurricane is, it's important to talk about the formation of a hurricane and how we get it. So some of the ingredients that we need for a hurricane to actually form is one, warm ocean waters. So with warm ocean waters, we kind of have our source of heat for hurricanes. So the warm ocean water helps to create the warm, moist air, and that's how we get thunderstorms. This air will then rise into the atmosphere, and with that, it forms clouds, and then it eventually forms a thunderstorm. And with this thunderstorm, we're able to get an initial disturbance, and you start to get more and more of these disturbances, which eventually form into one very large disturbance. And you get all these different thunderstorms that are eventually going to cluster together. And from there, we're able to get our tropical disturbance. And that's going to be our first stage when it comes to the life cycle of a hurricane or a tropical cyclone. So we start off with the tropical disturbance, and it's not very organized, but it is a very large cluster of thunderstorms. And once it becomes a little more organized and it starts to get a rotation, we get our tropical depression. From there, we're able to get a tropical storm, and that occurs when the winds eventually reach 34 miles per hour. And once it reaches that, it gets its name. And from there, once the winds get higher and higher, you eventually get a hurricane. And the winds have to be 74 miles per hour for that. And from there, the hurricanes can make landfall, or they can go out into the ocean and eventually fall apart and decay.
All right, so talking a little bit then about, as you could see in that last one, there's kind of a general track that Atlantic hurricanes typically follow. And that's shown here in this image as well. So usually in the Atlantic, we have disturbances that come off the continent of Africa. So they come off of the land and come over ocean. And like Morgan said, with that really warm ocean water, they can get a lot of heat, a lot of moisture, and that's where all those thunderstorms develop. And so as the track of them typically goes from east to west, and it can take any kind of curving that you're seeing that's shown here for the Atlantic hurricanes. Usually they kind of go up and around the coast, but occasionally some can make it into the Gulf as well. Like Morgan mentioned, Hurricane Michael, and then also Hurricane Katrina in the early 2000s. And so why exactly do they take that track? Why do they go from east to west? Why do they curve the way they do? And what makes them really move that way? So the main driver for hurricanes, there's a few other ones, but the main thing that really gets them moving in the way that they do is the global wind pattern. And so what we're looking at here is the different patterns of just the large scale winds that are associated with the Earth. And so between the equator and about 30 degrees north, or about kind of the top of Florida, you have these what are called the trade winds. And the trade winds blow from east to west or northeast to southwest across the continent. And so those are what really push the hurricanes in this general direction. And then as they get farther north, they get picked up by the westerlies, which instead flow from west to east or southwest to northeast. So if you kind of follow these arrows with my mouse, you can see you get that general curving pattern. Some other things that kind of change that or help move it away from that are if you have weather systems that move across the United States, those can kind of change the pattern or change how much it curves or how little it curves. But in general, the kind of main driving force here is this background global wind. And another way to think about that, or that's kind of a simple analogy for that, is if we think about leaves in a river. And so here the global winds or the background flow is the river, and the leaves are the hurricanes. So wherever the water is flowing, the leaf will follow or the hurricane will follow. So that's kind of if the river deviates to the left or tracks to the left, the hurricane, then the leaf will go to the left. Things like that. And so as we talk about tracks and how things move, the main organization that lets the public know about where a hurricane is going or where it might make landfall is the National Hurricane Center. They're based in Florida. And so they put out these graphics that are shown on the right that have where the storm is currently, that's that yellow dot. And then all of the following black dots are where the storm is kind of forecasted to go or where they think it's going to go next. And this gray circle around it is what we call the cone of uncertainty. And so there's a little bit of confusion about kind of what that means, what it's showing, because it can be tricky to get at first. So this cone of uncertainty is showing all the possible places that the center of the storm might be at that time. So as we'll explain in a little bit, forecasting is a tricky task, and there's a lot of uncertainty associated with it, especially the farther into the future that we go. And so what you'll see is, okay, near the storm, the cone is kind of really narrow. So where we think the storm center is going to be, we have it narrowed down to a pretty decent space. But the longer into the future we go, the more wide that cone becomes. So the more uncertain we are about where exactly the storm's going to go. And so the National Hurricane Center puts out these forecasts. They also can issue warnings associated with the storms to let you know what kind of hazards you might have, whether it's storm surge, really high winds, flooding, things like that. And the line in the middle of these is just kind of the average track that they're assuming. It's not saying this is exactly where the storm's going to go, but it gives some kind of an idea of where the middle of the road is.
So now that we know a lot more about hurricanes, it's important to talk about the impacts it's going to have. So the first thing we typically talk about when it comes to impacts is going to be the actual strength of the hurricane. We rate hurricanes based off of categories. So there's 5 categories in this scale, and they're all based off of the wind speed. So this isn't going to be talking about any other impacts when it comes to hurricanes in terms of category. So the lowest category is category 1. And although it is the lowest category, you can still have some major destruction associated with it. But one important thing to note when it comes to the actual categories of hurricanes is that it is not linear. So if you have a category 5 hurricane compared to a category 1 hurricane, the category 1 hurricane can be about 300 times as destructive as the category 5 hurricane can be about 300 times as destructive as the category 1, which means it gets way more destructive the higher category you have. So from there, we'd like to talk about other impacts. So we have storm surge. Storm surge happens when we have these really, really strong winds close to the surface that push on the ocean water. And as it's pushing more and more on this ocean water, it causes more ocean water to get on to the coastal areas. And depending on the strength of the hurricane, you can have a small storm surge of like 2 to 4 feet, but you can get like 20 feet of storm surge, which can cause devastating flooding and devastating damage to coastal areas. And do any of you guys know any hurricanes that had very strong storm surge? Leave anything in the comments. There's also wind. So a lot of times we think about hurricanes, we think about the very strong winds. Well, these very strong winds come from the low pressure. So in terms of the atmosphere, winds flow from a higher pressure to a lower pressure. Well, we have a very low pressure in the eye of the hurricane. So we get very, very strong winds right around the eye of the hurricane in the eye wall. That's where our strongest winds are. And these winds you can have gusts up to 250 miles per hour, which is a crazy amount of wind. And these winds can cause major destruction. They can knock down buildings, they can knock down houses, and they can toss trees around, and it can become very destructive. And we can also get pretty weak tornadoes in the rain bands of a hurricane as well, which is another wind damage. And here with these 2 videos, we have broadcast meteorologists who are like trying to stand up while being affected by these super strong winds, and they are clearly struggling. And you have Jim Cantori on the bottom, who can barely even stand up without holding a rope when he's getting to these super strong winds. And then last, but definitely not least, we have flooding. So as of recent years, we had 2 major flooding events that occurred in 2 different hurricanes. So we had Hurricane Harvey in 2017 and then Hurricane Florence in 2018. Both of these hurricanes had an extreme amount of rain that fell. In Hurricane Harvey, we had dozens and dozens of inches that fell near Houston. And then Hurricane Florence, we had dozens of inches that fell in North Carolina. And with this flooding is caused by the hurricane that slows down to a really slow speed after it made landfall. And because of that, the hurricane that has tons and tons of moisture is able to just drop all this rain, and you get this really high flooding event. And flooding is one of the leading causes of death when it comes to weather impacts. So it's important to note and to know what to do if you do experience flooding that happens during a hurricane. So if you do come across a flooded road, you should turn around and not drown.
So now that we've gone over a lot of what hurricanes are, what they have, what their impacts are, we're going to talk a little bit about forecasting. And this is where it gets a little heavy in some of the math and the numbers, but we'll keep it simple. So the biggest way that we can forecast for storms is using what we call numerical models. So numerical models are a combination of taking observational data. So for meteorology, we have a lot of different ways to take measurements of a lot of different atmospheric variables, whether it's temperature, moisture, pressure. We have a lot of different ways to take those measurements, whether they're ship measurements. You can use radar, satellites, aircraft, things like that. So we have access to a lot of different observational data all the time. And also in atmospheric science and in meteorology, we have a lot of very complicated equations, calculus and such, kind of gross to look at. We have a lot of these difficult equations that make up and define the atmosphere and define how things move, how air moves, and kind of the basic atmospheric qualities. So what we do is we take these really complicated math problems that would take way too long to solve by hand and would be way too complicated to solve by hand. And we couple them with the observations, and we basically give it to a computer, and the computer tackles it. It solves the problems, it solves the equations. And as it's going through all of these calculations, it gives out forecast data. So it tells us, okay, this is what the weather was like currently, and this is what it's going to look like hours and days from now. And then we can take that forecast and put it into kind of visualized data. So this is a forecast that was made it was made overnight last night, but it's a forecast for Monday at around 1 o'clock. And so what this is showing is that Monday around 1 o'clock, it will be beautiful in Raleigh. We'll have some nice like mid to upper 70s temperatures, things like that. So it took the observations from last night, put them in with all the gross math problems, and it gave us a forecast for Monday afternoon. And so meteorologists use this for all kinds of things. So it forecasts all things about the weather, and we can use this for hurricanes as well. So any observations they take of the hurricane, whether it's the wind speeds, the pressure, we can put that back into hurricane models, and that'll help you forecast a better track for it in the future. So along with using these numerical models for forecasting, Morgan and I also use them for research. So in the same way that we took observations and put them into the model, we can take observations from any point in time and put them in the model. So instead of taking the observations from last night, Morgan and I take observation data, any kind of measurements like that, from farther back. So I'm looking at a storm from 2016, and Morgan's looking at a storm from 1996. So we're taking the observational data associated with those storms, we put it in all the equations, and then we get back out what's kind of like a forecast or a reforecast since the event already happened. And so this is an example of that. On the left is kind of the output we get from our numerical models. So we get this, what we're looking at here is what's called reflectivity, which is if you've ever seen on your local news station when they show rain, kind of like what's shown here on the right, the more warm colors are associated with heavier precipitation, and the cooler colors are kind of that lighter precipitation. And so they're a little off from each other time-wise, but as you can see, when the simulated storm gets really close to the coast, it looks really similar color-wise to what the actual storm looked like. So with these numerical models, we can get really realistic simulations of weather events. And so now we're going to dive in a little bit and give you guys an introduction to what kind of research we're doing in grad school and what we're looking at as it relates to hurricanes. There we go. So for my project specifically, I'm looking at how precipitation associated with hurricanes, so the rain that falls with a hurricane, how that might change with climate change. So we know that the climate is changing, we know it's getting warmer, and that has different impacts to different types of storms. And so we're really interested in how it's specifically going to impact hurricanes in North Carolina. So my project, we're partnered with the Department of Transportation. So what we're looking at here are all kinds of roads across North Carolina that have flooded or been washed out from hurricanes over the last 6 years. So we had Hurricane Matthew in 2016, Hurricane Florence in 2018, and Hurricane Dorian in 2019. So all of these storms caused a lot of damage to roadways. Some of them broke apart or got washed out. Major highways were flooded for a couple days at a time, really halting traffic and making it difficult for people to get the help that they needed. And so the Department of Transportation noticed this, and they said, hey, we really got to work on this. You know, we don't want to have to keep rebuilding roads. We don't want this to keep happening. So they want to know what rain might look like in a future climate so that they can build their roads to prepare for it. And so that's kind of where our project comes in. And that's where this numerical modeling can be really helpful. So a good way to compare what rain might look like in the future with what it already looked like is to use a storm that we know was really impactful. We know that had a lot of rain the first time around. And so the storm we're using for my work is Hurricane Matthew, which some of you might remember from 2016. It didn't actually make landfall in North Carolina, but it kind of rode right off the coast and caused a lot of rain to fall in eastern and kind of central North Carolina. And so the same way as before with those numerical models, but now our observational data is all of the data that was associated with the time that Hurricane Matthew happened. So we're taking data from October 7th, 2016, giving it to all these equations, putting it all in, and giving it to our computer to solve. And then what we get out of it is a simulated storm that looks a lot like what the actual Hurricane Matthew did. So if you remember from that last slide, it takes a track that kind of goes up along Florida and then curves around North Carolina and drops a lot of rain across North Carolina. And this is again showing that reflectivity where the warmer colors are the really heavy rain. So a lot of North Carolina got those warm colors for a good amount of time. So once we have those simulations, we can also do something like that for a future climate. So this is where it gets, again, a little complicated, a little complex, but we have the same storm, our same Hurricane Matthew observation, but now we're making the storm look like what it would 100 years from now. So we have ways to update the storm environment, so what the atmosphere looks like and what the temperature looks like on any given day. I apologize for my cat in the background. So we have ways to make the atmosphere and the temperatures look like the future. And so we do that with these storms, and then we're able to see what the differences are between them from a rainfall perspective. So the first time Hurricane Matthew happened, we had regions that had 10 to 15 inches of rain across eastern North Carolina, and some that had 15 to 20. And now with our future simulated storm, so where we took that warmer temperatures, things like that, we have a lot more rain across eastern and southeastern North Carolina. So the Department of Transportation is really interested in that because if they can expect these kind of really high rain amounts, then hopefully they can build their roads and their bridges to be prepared for this in the future.
I'm doing a project that's also pretty similar to Katie's, but I'm looking at wind. So what my motivation is we're believing that hurricanes post landfall are when many of the significant damages occur. So we care about the low-level winds that can be extremely destructive, but they don't have a lot of data due to damaging stations after the hurricane makes landfall. But we're looking at hurricanes in the future. So we are predicting that these low-level winds are going to cause even more damage in the future because of the climate being a bit warmer. So I'm particularly looking at Hurricane Fran. Hurricane Fran made landfall in 1996 at Cape Fear, North Carolina. And it was specifically known for having really strong winds inland, especially in the Raleigh area, where they experience about a week of no power. So we're putting Hurricane Fran and we're simulating it in the present, similar to what Katy's doing. And then we're also putting Hurricane Fran in the future. And we're going to be looking at the winds from landfall to 24 hours after landfall. We're trying to see the decay rate. And this decay rate is based off of how fast the winds are going to be dying down after landfall. We're predicting that the winds are going to be dying down at a slower rate after landfall, which would then cause even more damage to more inland populations. So we were able to model Hurricane Fran, and on the left graphic, we see that this is just showing winds at the highest winds at any particular location within the model. And we can see that there's the path of the hurricane shown. So those brighter colors, you see like the lighter blue, you can see a bit of like orangish, and those are going to be high winds. And those high winds are the winds that are coming from this model of Hurricane Fran. And on the right, which was the same GIF earlier in the presentation, that's where these winds are coming from. It's coming from this simulation of Hurricane Fran. So what we're looking at is seeing how fast these strong winds are dying down. So we're still working on the results, but they look promising. And now that you know about our research, if you want to get into atmospheric science, but you don't particularly want to do what we do, there's actually a lot of different careers. So in a more hurricane-based career, there's hurricane hunters. And these hurricane hunters are the people that will fly into hurricanes and they'll get a ton of measurements. So learn about how low the pressure is, which helps to determine the strength of the hurricane. And they'll get all these different measurements. And then we take those measurements and we put them into models, and we're able to predict the hurricane's track, and we're able to predict more of how much the hurricane is going to impact. You can also be a professor if you want to major in atmospheric science, and you'll be able to teach students, and you'll be able to do some of your own research as well. And that's going to be the academia side. And then you can go into insurance, because insurance companies care a lot about what atmospheric scientists know, because that determines some of the rates for flood insurance, that determines the rates for coastal areas. You can also go into National Weather Service, and you'll be able to do the day-to-day forecasts that go into different people's models, and that also help emergency management, which is another career that you can go into. And with emergency management, you'll be able to help people during severe weather events. And then finally, but last but not least, you can also go into broadcast meteorology, where you could be a broadcast meteorologist on a local channel. And as of late, there's been some online broadcast meteorologists as well. And thank you so much for listening to us. And that is the end of our presentation. If you have any questions, you can ask them in the chat, or if you have any other lingering questions, you can email us as well.
Thanks, Morgan and Katy. The floodgate is now open for your brainstorm of questions. Please place your questions in the chat or tag us on our social media accounts. We will try to get to as many questions as we can. Okay, first question. What mitigation can be done for upcoming changes in the climate regarding hurricanes?
Yeah, that's a great question. So that's kind of at the front of what we're trying to figure out with climate change. So that's not necessarily our realm. We focus mostly on, what the weather is going to do, how that's going to change. But some things to consider, I guess, if you're looking for a future climate, if we're expecting more rain or stronger winds, that'll be changes in kind of how you build buildings. If you're looking at changes in flooding, it's like how high do we build this bridge, or how do we kind of change the roads or the drainage of things. So it's a great question, and something that's definitely still in the works of in engineers and hydrologists, and also, like I said, on the transportation side of things as well.
Great, thank you. Second question, regarding the naming of hurricanes and forecasting for the hurricane season, how active is the upcoming hurricane season forecasted to be?
They tend to put out the forecast for the upcoming season around May, once the ocean starts to warm up a bit more, once we kind of know what's going to happen. So we don't know yet for the upcoming season. But in terms of naming hurricanes, National Hurricane Center has a list of names that they cycle through. So they go through all the names, and if they get all the way to the bottom, they then go into Greek letters, and then you don't really go past that. But occasionally we'll get names that will be retired. If the hurricane caused enough damage, they'll get rid of the name, and then it gets taken off the list for future years.
Interesting, thank you. A question from Hugh Allen. How far out can weather be predicted?
So that's a great question. Technically, you can make forecasts out a long ways, but in terms of forecasts that you can make, I guess, with a lot of confidence, it's really only a couple of days. Outside of kind of 4 or so days, you really, there's just so much, there's a lot of uncertainty with all of the equations that are going into it. We kind of make assumptions about things, and there's just a lot of error, and the chaotic nature of the atmosphere makes it really hard to forecast past like 4 days. The analogy I've heard of kind of explaining how chaotic the atmosphere is imagine you're in an airplane and you drop hundreds of thousands of bouncy balls out of the plane, and you're trying to forecast where every single bouncy ball is going to go, how it's going to interact with the other ones, things like that. So it's really, really chaotic. So I'd say outside of about 4 days, you kind of lose a lot of confidence in the forecast.
Great, thank you. Another question, have you ever been storm chasing? And if not, would you be interested in storm chasing?
I have not been storm chasing. It's not the safest to storm chase around the South, especially the Southeast, just because we do have a lot of really tall pine trees. And if there's a tornado, it could be like 100 yards away, but you wouldn't be able to see it because there's a ton of pine trees in their way. So you don't really have time to get away from it. But I think it would be cool to storm chase. But as atmospheric scientists, we're not really supposed to encourage it because it's not safe at all.
Great, thank you. And then have you ever been in a hurricane or experienced the effects of a hurricane?
So growing up for me in Southeast Pennsylvania, we never really got the actual hurricane happening. By the time that we got any bit of hurricane things, it was kind of like the remnants. So it was mostly just a lot of rain, not really any strong winds, not a crazy amount of flooding. But I guess last year we got a hurricane, or 2020, we got Hurricane Isaias, I believe. So I guess I did experience that one, but I haven't really been through anything crazy.
And what about you, Morgan?
I have sort of been through a hurricane. It wasn't a hurricane by the time it hit us. I lived in North Georgia, and once Hurricane Irma made landfall and then went straight up, Florida, I was at the University of Georgia, and we ended up getting really, really strong winds, which kept us out of school for 2 days. I think gusts were around 60 to 70 miles per hour. A lot of trees fell. And then the next year, Hurricane Michael hit, and we also got really strong winds, although that hit overnight, so I didn't really see as much of it.
Interesting, thank you. Yeah, growing up in North Carolina, we mostly just got the rain effects of the hurricane. So next question, what has been your most interesting hurricane to study?
That's also a good question. So the 3 storms that I'm looking at are Hurricane Florence, Hurricane Matthew, and Hurricane Floyd. Floyd was back in 1999, so most people probably don't remember it. But for me, I would definitely say Hurricane Florence is the most interesting I've studied, just because it slowed down so much as it got towards the coast, and it just kind of parked there for a little bit and came up really slow and just dropped so much rain. So from kind of a flooding perspective, it's really interesting to study how much rain actually fell, what that might look like in the future, how much rain might fall in the future. And also kind of where that rain went when it hit the ground, what flooded, what didn't, things like that. So for me, it's definitely Hurricane Florence.
And what about you, Morgan?
For me, I would say Hurricane Michael. I ended up doing a lot of research beforehand with Hurricane Michael as it was like approaching landfall. And then I helped to brief emergency managers in Athens as it was approaching, just so that they would know about the winds and they would know how they should prepare beforehand. And then I also did even more research after the fact at National Weather Service, where I looked into the communication of Hurricane Michael and how the National Weather Service stations in Tallahassee and the National Weather Service station in Atlanta had communicated the risks in terms of Hurricane Michael. So I'd say Hurricane Michael is that's my pick.
Great, thank you. Another question, what is your favorite part about studying hurricanes?
So for me, it would definitely just be, I guess, realizing how much power and how much energy they have for kind of one storm system. They're just the amount of damage they can do in such a short amount of time, especially with those really strong hurricanes, the really like Category 4, Category 5. It's just really impressive and definitely scary how much of a punch they can pack. And so I'd say that's the most interesting part for me, is just studying the impacts that they have and how they affect people's lives, so that we can better understand them and hopefully better forecast them in the future and try to prevent that kind of damage and loss of life as much as we can.
I would say that my favorite part is just really seeing how expansive hurricanes are. They're very massive storm systems, and a person like 50, 60 miles away from each other, they can have like equally as strong damage in their location. And it's just quite amazing to see how strong hurricanes are. Although the impacts are very scary and they're very serious, I do get excitement with hurricanes. They're very exciting.
Thank you. A question from CH Bell 99. How does ocean temperature affect hurricanes?
Yeah, so I can tackle that one. Ocean temperatures are kind of the fuel for hurricanes. So you need those warm ocean temperatures, because when the ocean's really warm and the storms kind of move across it, the warm waters evaporate, and that is how a lot of the moisture from the ocean gets into the atmosphere and into the storm. And so all that moisture that's coming from the ocean to the atmosphere is what can make it, is what provides that energy for the hurricane and like all that rain that you can see in the aftermath. I think Morgan had the slide up that was about, you need about kind of 80°F or warmer is kind of the rough estimate number for the temperatures you need in order for that kind of evaporation to occur and those storms to really survive. And that's kind of part of the reason that as storms get farther north, they really weaken a lot because they don't have those warm waters. They don't get as much moisture from them that kind of keeps them fueled and keeps them going. So that's kind of the point where they end up fizzling out a little bit.
Great, thank you. Another question from Hugh Allen. What state is likely to receive the most hurricanes over time?
I'll take this one. I would say that there's no particular state that would receive the most amount of hurricanes. It really just depends on other factors. Like Katie said earlier in this presentation, the track of hurricanes is dependent on the background flow. So if you have a stronger background flow that leads more towards Florida, you're going to get a hurricane that's going to make landfall in Florida. Or if you have a background flow that leads towards like Louisiana or leads towards Texas, you're going to get one there. So you're not really going to see any particular place get more hurricanes, but yeah.
Okay, thank you. A question from Ryan. Have hurricanes in general gotten worse or better in the past decade? So I guess he means more severe.
Yeah, I can tackle that one. There's been a lot of research lately coming out about how hurricanes have changed kind of over the last, usually it's over longer time periods, so over between like the 1980s to now. And some of kind of the things that are coming out about it is that there's different trends, but different studies kind of find different things. So there's as you go farther back in time, it's harder to account for how many hurricanes there are or what strength they got to, because we could only take record of the hurricanes that made landfall. If there were hurricanes over the ocean, you might not have seen them or might not have counted them. But in general, there is could be seen kind of a slight trend towards some of these stronger hurricanes. And as you project into the future, they're expecting this trend towards more or less hurricanes, but more that are kind of that stronger intensity. And that can kind of be tied back to those warmer ocean temperatures, because as you have the climate warming, the ocean temperatures are also warming, and that gives a lot more fuel for these storms to get going. So those are kind of some of the trends going forward. In terms of wind speed, it's kind of associated with the intensity. So like the more thunderstorms you get going, the kind of more the stronger that storm can get, and then the higher category you might get. The biggest trend is with more precipitation, I would say. That's kind of the most obvious connection, is that if you have more moisture from the ocean, there's more that can dump on the land when it makes landfall. Hopefully that answered that.
Yeah, thank you. Interesting. So a question from a summer pup. Do hurricanes tend to happen more after a certain type of weather or temperature?
I would say hurricanes aren't really going to be dependent on like the weather going on, like at least on continental United States. We'll see hurricanes form in the ocean and you get thunderstorms in, but I would say it doesn't necessarily happen after any particular event.
The one thing I'll add to that is that, like we said before, a lot of the storms kind of originate from Africa. So they're kind of tied to those disturbances over Africa, at least for part of the hurricane season. So in terms of US weather, yeah, like Morgan said, there's not a ton related to kind of the weather we experience on the continent, but the storms that happen over North Africa are a big determining factor for what'll happen with the hurricane season.
Oh, interesting. Okay, so a question from PopKernel88. How reliable are weather predictions based on how far out the prediction is made, and how do forecasters decide how far ahead to predict weather?
So a lot of times the length of a forecast that a different company or organization will make kind of depends on what the people they're making the forecast for want. So if they're a private forecasting company, if they have people that want forecasts out like a month or two, then they can make those forecasts. Like I said before, there's a little bit less confidence the farther out you go, just because the atmosphere is so chaotic. But in general, forecasting out, they make a lot of the models forecast out a couple weeks just to kind of get an idea of what the atmosphere might look like. And then you can kind of watch how it changes or how it's trending in order to get more confidence as it gets closer to that time. But yeah, like I said, confident forecasts are usually only in the kind of short term, but the length of it depends on what companies' kind of constituents or what the people they're making the forecast for want or what they need for it.
Great, thank you. And then another question from a summer pup: does the hurricane get bigger if the ocean temperature is higher?
I would say size isn't really dependent on the ocean temperature. It's basically a hurricane by hurricane basis. Some hurricanes can get really, really big, but then you can see very strong hurricanes. For example, Hurricane Maria. It wasn't enormous, but it was extremely strong. So size isn't necessarily dependent on the temperature, but you can get more thunderstorms associated with hurricanes in a warmer temperature, but that won't necessarily cause a larger hurricane.
Great, thank you. And then a question from Shauna: do hurricanes only happen in the ocean, or can lakes also have a hurricane?
So that's a great question. One of the other factors kind of controlling if a hurricane forms or not is the storm being close to the equator. This is something we didn't go into because it gets a little complicated and has a lot of background explanations, but part of the reason you wouldn't get hurricanes over lakes is because they're so far north. And so the other factor is that lakes are so much smaller that the storm wouldn't spend enough time over the water to get to the strength and the intensity that a hurricane does. So like the longer the storm is over water, that usually can help it maybe have a chance to get stronger. But yeah, since lakes are so small, they can't really form hurricanes. You can get other weather phenomena from lakes, like lake effect snow. So lakes can enhance precipitation or make make it rain more or less. They can kind of interact with smaller scale weather. But no, you couldn't get a hurricane on at least not one of the US lakes.
Great, thank you. And then another question from Hugh Allen: is there a record of the heaviest weighted object a hurricane can lift?
Admittedly, I don't know that off the top of my head. I'm sure that the way that they look at kind of hurricane wind speeds are the damage it does to structures. So like a category 1 starts to rip shingles off, or like a category, a higher category might like uproot trees. But I don't actually know the answer to that.
Great, thank you. And then what is your least favorite part about studying hurricanes?
I would say my least favorite part, which kind of ties into my favorite part, hurricanes are huge, and there's a lot of stuff that goes into what forms a hurricane and what maintains a hurricane. While we did our presentation today, it's extremely complicated how hurricanes form, and there are like disputes with certain things about it because it is a growing subject and people are still learning a lot of new stuff about it. So I would just say, because there's just so much stuff that goes on with hurricanes, it can be just extremely complicated, which makes it a little more difficult to learn about.
And then Katie?
I would say my least favorite part is just that usually the storms that we study have caused a lot of damage. That's kind of why they're known and why people are interested in them. And so that's kind of, it's very sad to see all of the devastation that hurricanes can cause, especially if it's in your state or in your hometown. Kind of seeing the areas that get hit by these things can be really very sad and very hard to deal with sometimes, and hard to balance with the research.
Okay, last two questions from the YouTube chat, one from CH Bell 99. Why do hurricanes rotate?
So this gets into some of the stuff that we didn't mention just for the sake of the presentation, so it wouldn't be too complicated. So because the Earth rotates, very large storm systems rotate, and that's called Coriolis. So as you get farther away from the equator and farther away and closer to the poles, you get more rotation. And because of that, once you get a very large storm system, like these clusters of thunderstorms, they can start to rotate. So that's how we get our rotation.
Great, thank you. And then this question kind of ties into it, but how fast do hurricanes swim from a summer pup?
Did you say how fast do they swim?
How fast do they spin? Sorry.
Spin. Okay. Sorry, I just want to make sure. So hurricanes have the way that we kind of measure the spin is also the way we measure the wind speed. So the winds in a hurricane are blowing circular around it. And so kind of the strongest storms, so if you get up to like a category 5, those are greater than like 157 miles per hour is their kind of the wind that's spinning around them. Most don't get up to that category. Most kind of linger around the middle of the lower categories. So somewhere between that 74 mile per hour, that makes it a hurricane, but not quite getting up to that 157 mile per hour.
Okay, thank you so much, Katie and Morgan. Now passing it off to the closing statements. And I'm sorry again for being unable to answer all of your questions. We will drop Katie and Morgan's emails in the YouTube chat in case you have extra questions to ask.
Thanks again, Morgan and Katie, and thank you all for watching. I hope you were blown away by everything you learned today. We would also like to thank the museum's digital media team for helping put on the cafe. Don't forget to follow the Teen Science Cafe and mention us on Twitter, Facebook, and tag us on Instagram. Check out the QR code on screen or use the link in the chat to complete our survey. The survey will also be sent in a follow-up email that you registered with. Completing the survey enters you into a drawing for a $10 e-gift card of your choice to Amazon or Starbucks. Be sure to complete the registration form and tune in for next month's cafe on Friday, April 1st at 6 p.m., where we'll be hearing from Joshua Pierce as he explains the chemistry of making medicine.
Thank you for joining tonight's Teen Science Cafe. If you haven't already, make sure to subscribe and hit the like button. And make sure to hit the bell notification button to make sure you don't miss any premium content from the NCMNS. Don't forget about filling out the cafe survey because your feedback matters, and you'll be entered into the gift card drawing. My name is Rayon, and these have been your cafe coordinators. We can't wait to see you next month, scientists. Have a breezy and fun March.